Hi all. In this video, we are going to see a paper titled Low Rank Adaptation of Large Language Models. So we'll see what this paper says about. Uh, we all know that natural language processing requires very large models with large number of parameters. Like, for example, ChatGPT requires 175 billion trainable parameters, which are pre-trained, and later they are fine-tuned for different multiple applications. And during the fine-tuning, all those big number of parameters are updated, which poses very inconvenience during training. So in order to alleviate this, many techniques are followed. One among the technique is to focus only on a specific number of parameters during fine tuning. Then there are many techniques adapted to how to choose those finite set of parameters during the fine tuning for specific applications. In this paper, they have proposed a new technique called LoRA, based on hypothesis that during that fine tuning, only certain low rank adaptations are required. It means that when we are updating that model parameters for the fine tunings, only a small number of parameters which lies in a low dimensional manifold are required to adapt for that specific task. So this is been very clearly very simplified rank 1 update techniques from numerical linear algebra. So we all know that neural networks have many number of dense layers in large language models, and each layers requires matrix vector multiplications, and the matrix is weight matrices, and that has to be updated during the fine tuning. For example, the pre-training matrix can be represented as W0. If this W0 is updated for every fine tuning task, then it's called as full fine tuning. But in case of only to adapt for a few parameters, we put up in this setup where delta W is updated, but so that the new update would be related to W1 or something is equal to W0 plus delta W. So this delta W again is have a matrix decomposition of BA, where BA is like kind of very thin matrices along the column, and A is a very thin matrix along the row. It is something like matrix along the column. So for example, B is D cross R can be any size which is very less compared to D or K. So D is number of rows in the pre-trained weights, and K is the number of columns in the pre-trained weights which are whose dimensions are very large compared to R can be, for example, one. Then it will end up in BA multiplication will end up in a rank 1 update. So when doing matrix vector multiplication, we're multiplying with the input, the new updated matrices, it would end up with the decomposition, something like that. The original matrices won't be changed as it is, which can be already multiplied and can be set in memory stored. And this only needs to be updated where it can be ended up with this one. So it's a very simplified technique, but a powerful numerical algebra technique for which helps us to fine tune the many large language model applications without computational overhead. So the initialization can be a Gaussian initializations, and that can be updated during Adam thing. So this is for particle dense layer. Then this can be adapted for all those layers in the large language models. So that's all this about this paper, and this setup is beautifully represented in this figure 1. So this is a weight matrix, and these are the thin matrices A and B, which where this input is multiplied in both directions, and the final output of H is been given to the further in-depth layers. So hopefully you'll see some other papers based on this best tips paper being updated in 2023 that we will try to see in the next video. Thank you.